Okay, so once again we see this picture. We've seen it so many times now. I'd hope that we understand it, but I have a metaphor, as it were, to help us understand what's going on. So the metaphor is on page 125 of your manual. And here it is. So it goes on. Suppose you have a poem written in English. Look, you can see that there. I'll just, so that's on page 125. I'm going to go back to this. So the metaphor that I use is you have a poem here, and it's written in English. And what you want to do is find out what the poem means, and that would be the analog of solving the differential equation, and that's difficult. But perhaps you know a French person, in the metaphor is called Pierre Simon. That's Laplace's actual name, Pierre Simon Laplace. And the idea is that you translate your poem into French, and Pierre Simon has no problem interpreting the poem and finding the meaning in French. And all you have to do is to translate the meaning from French back into English. So this is my metaphor for what's going on here. Now, in that metaphor, translating it into French, giving it to someone French, and they're more poetic and they can understand it, we turn what we do, rather than going from English to French, we go from a differential equation to an algebra equation. And we'll write this now on page 125. Derivatives get turned into multiplying by s. So this is also in your big table. So this is down the bottom of your big tables. Well, somewhere in your big tables. So the Laplace transform of first derivative is, so the translation, if you differentiate a function, it multiplies it by s over in the s domain, and then you also have this minus f of 0. If these formulae are kind of mysterious to you or anything like that, if you go, there will be a section, now I don't know where it is, you'll have to probably go to the index that derives all these formulas and show exactly where they come from. Basically where it comes from is differentiating an exponential in e to the minus st, respect to t would be minus s. So differentiating in e to the ax, as it were, is a times e to the ax. And that's where it kind of pops out of. The other one is that a second derivative, now differentiating twice, should turn into multiplying by s twice, in other words, s squared, fs minus s times f of 0 minus f dashed of 0. So these are precisely how different derivatives get turned into algebra, basically, is what we're talking about. The basic 4 steps are here. When you have a different, now we may as well write down this linear differential equation. Basically, you're talking, most of them be roughly this shape. So a constant times a second derivative plus a constant times the first derivative plus a constant times the function you're looking for is equal to some function of time. I'm fairly sure all of them roughly can be written like this. Some of them won't have they'll have missing terms. So anyway, so you take the Laplace transform on both sides, you turn it into an algebra equation, you apply the initial conditions. So the initial conditions are the initial value of the f, the initial value of the f dashed. You solve for the Laplace transform of the solution, that's the easy bit, and then the medium difficult bit is sending it back by applying the inverse Laplace transform. So we're going to do a number of examples of this. Okay, so beginning here in autumn 2017. Now, one of the things, you need to have this picture in your head a little bit. And so this one, we've got a function of x. So we're going from a function of x to a function of s. It's either going to be x or t here, it's always going to be s here. and our Laplace transform goes from here to here, and the inverse Laplace transform goes backwards. And we take the Laplace transform of both sides. That's your first step. So the other thing we may as well write down when we're here is if you have a little b of x, it'll be transformed to a big B of s. And we will, some authors will use a little b of s, but I think it's a little bit safer to say a big B of s. Okay, so we take the Laplace transform of both sides. Now the second derivative here, we're using this formula here, but we have a second derivative with respect to x. Now that's okay, so these are similar, but instead of f's all the time we have b's. So we should have s squared big B of s minus s little b of 0 minus b dashed of 0. So the role of f is being played by b, which in this question is the bending moment. So we take the Laplace transform both sides, we get s squared, not big F of s, but big B of s, minus s times little b of 0 minus b dashed little b dashed of 0. So this is the Laplace transform of the second derivative, and a constant, if you look in your tables, is sent to a constant over s. Okay, so that's the first step. We've translated the differential equation into an algebra equation, which is far easier to solve. Now what we do is we implement the initial conditions. So the bending moment at 0 is 0, so this is going to be 0. And then the derivative of the bending moment at 0 is 36. This is going to be 36. So we get s squared big B of s times 0 is just 0. Now I'll just put it in for now, just in case you're looking at it. Minus b dashed of 0, b dashed of 0, as you can see, you'll be given in the question, is 36, equal to minus 12 divided by s. So that's the baby little step of just putting in the initial conditions. Now this is not s of 0, it's s times 0, so this is 0. Gone. So now what we want to do is we want to solve for big B of s. So rather than this differential equation, we have a little algebra equation. So what I'm going to do first is I'm going to add 36 to both sides. And I get s squared big B of s equal to 36 minus 12 divided by s. And now this is probably the trickiest part here, dividing by s squared. Now what you have to know is that if you've got a sum and you're dividing it, you have to divide both of them. So say for example you and your friend find 100 euros plus 20 euros. How do you share it out? Well, you'll divide out the 100 euros by 2 plus the 20 divided by 2. So that's the first thing. So dividing both sides by s squared, both of these separately will be divided by s squared. The other thing then is, how do you do a fraction divided by something? So this isn't necessarily that difficult or this easy. And so maybe if I take something like 20, or we'll say 40 divided by 2, and you want to divide that by, let's say, 5. How do you do this? So I think probably the easiest thing is, there's different ways of going around and about this, but I think the easiest is just to kind of tell you how it works. I can convince you in other ways that this is how it works, but anyway. So it'll be 40 divided by 2 and also divided by 5. Now this isn't very convincing at the moment, and what I'm going to say next shouldn't be too convincing either, but we'll see. So 40 divided by 2 is 20, and 20 divided by 5 is 4, so this should be 4. And if you look at this, 2 by 5 is 10, 40 divided by 10 is 4, you get the same thing. If you really want to see why these are equal, dividing by 5 is multiplying by a fifth. So you got 40 over 2 by 1 over 5, top gives you 40, bottom gives you this. So ultimately, if you've got a fraction divided by something else, say 12 divided by s, it'll also be divided by s squared. So what I'm going to do now is I'm going to divide both sides by s squared. So bs b of s by s squared divided by s squared is b of s equal to 36 divided by s squared, and now I have minus 12 divided by s and also divided by s squared. Now the 36 over s squared is no problem, we are going to be able to send that back. But this one, well, what's s by s squared? Pause and have a think if you want. S by s squared is s cubed. Both of these are in the tables because we have in the tables that 1 over s to the n goes back to inverse Laplace, sorry, is t to the power of n minus 1 over n minus 1 factorial. And if you did that, it wouldn't be too bad, but notice that we've gone from x to s. When we're going back, we're going to go to x. So instead of t's, here we're going to have x's. So the inverse Laplace transform of big B of s is little b of x. And actually here, what are we doing to both sides? Well, we're doing the inverse Laplace transform. So 36 divided by s squared. Now I can fix the 36 as a constant, and 1 over s to the 2 goes to, now not t, but x to the 2 minus 1 divided by 2 minus 1 factorial. Fix the minus 12, and what about 1 over s cubed? It goes to x, so 1 over s to the 3, x to the 3 minus 1 over 3 minus 1 factorial. And 2 minus 1 factorial is 1 factorial, which is 1, so this is 36. 2 minus 1 is 1, x to the 1 is x. And then we have, okay, what have we got here? 3 minus 1 is 2, 2 factorial is 2 by 1 is 2, so we have 12 divided by 2 is 6, and x to the 3 minus 1 minus 6x squared. So that is your first full exam question for Laplace transforms. Now as they go, that is an easy one, but it's done. Okay, so question 1 done. Right, let's see another question. So what do we got here? The velocity vt of a parachutist subject to linear air drag t seconds after falling out. Okay, so one of the good things here is it's a function of t. So we're going to go from t to s and back to t, is given by this differential equation. Solve the differential equation using only Laplace transforms. So yeah, in these exam questions, you have to use the Laplace transform method, otherwise you get 0 marks. So the first step, we translate this differential equation into an algebraic equation. Now this time, the role of f is being played by v. Okay, so whenever you see f's in the tables, it's v's. How do I know that? Because it's dv dt, df dt, and f of t, v of t. Okay, so do the Laplace transform both sides. Now here we've got a first derivative, and going back to the back of your tables, what happens to a first derivative? It's s times the Laplace transform minus little f of 0. Now here it'll be v dashed dv dt is sent to s big V of s minus little v of 0. So taking the Laplace transform dv dt using that formula, we have s times big V of s minus little v of 0 equals. Now 9.81 is a constant, so it will be sent to, using the tables, a constant over s. We'll just make a note of that here. In the tables, a constant gets sent to, by the Laplace transform, a constant over s. Minus, fix the constant 0.025, and what is little v of t sent to? Little v of t is sent to big V of s. Just like little b of x is sent to big B of s, little v of t is sent to big V of s. So that's the first step. This is now an algebra problem. The second step is you apply the initial conditions, that v of 0 is equal to 0. So that just is basically, well, strike that. It'll be s times big V of 0, big V of s minus 0 equal to 9.81 divided by s minus 0.025 big V of s. That's the second step. And now you want to solve this for big V of s. So this is something we haven't quite done. So if we're trying to solve this for big V of s, you're going to get V of s on one side and a function of s on the other side. So usually we're going to maybe get the v's over here. So I need to get this out of here. And how do I get rid of this? Well, I add this to both sides. And this is probably going to be done on the next page. Yeah. So solve for big V of s. So this is, I'm going to add this to both sides on the next page. So we may as well write it. Plus 0.025 big V of s. Add that to both sides. We get s times big V of s plus 0.025 times big V of s is equal to 9.81 divided by s. Okay. Now we're trying to solve this for big V of s. Now the next thing, if we're in class, I'll try and tease it out. But here I'm just going to tell you, when you got this kind of a situation, what you need to do is you need to take out the common factor of big V of s. So we'll do that. So take out the common factor of big V of s, and you're left with s plus 0.025 equal to 9.81. And for space, I'm going to write the divided by s like that. And now what we want to do is divide both sides by this. And sure, we'll write it down here as well. I'm going to divide both sides by s plus 0.025. So we end up with solving big V of s, which is Laplace transform the solution. So we've got 9.81 divided by s, and now also divided by s plus 0.025. Okay, so this is the first 3 steps done, and now what you want to do is send this back. Now if you're looking at this and you see, oh, I can send a constant over s back to a constant, and I can send, say, 1 over s plus a back to e to the minus at. Okay, while that is valid and both of these inverse Laplace transforms, we're going to need them in a moment, I can't do it at the moment because this is all multiplied together. I'm only able to apply Laplace, inverse Laplace transform linearly, which means I can apply it to a sum. I can't apply it when it's things multiplied together. So you got all, this is a situation where you've got things multiplied together. You need to write this as a sum of simple things. And that means you need to do partial fractions. And the first step to partial fractions is you factorize the bottom, and thankfully that's done already. And now I ask you, what rules have you got? Now, so what rules is this? What rule is this? If you want, pause the video and have a little think. So this is a rule 1, because it's an s plus something. Now s on its own doesn't look like a rule 1, but it is. It's like s plus 0. And if it's 2 rule 1s, then you can find the constants straight away. So we're going to have v of s using the cover-up method. Now if there's any rule 2 or rule 3 around, you cannot use the cover-up method. So v of s equal to, you can have some constant divided by s plus some constant divided by s plus 0.025. So I might need to grab a calculator in a moment. So for the s one, what you do is you say, okay, well, we'll do this one first actually, because the s is actually a bit confusing. So you're going to cover this up, but before you do, you say, for what value of s is this equal to 0? And the answer is minus 0.025. And now you cover this up, and into everything that's left over, 9.81 divided by s, whenever you see an s, you put in that value of s that makes the bottom 0, which is minus 0.025. Okay, I'll have to go to the calculator in a second. Then for s, so this, it should actually be easier, but it's a little bit confusing. For what value of s is s equal to 0? You can have a little think about it, pause the video perhaps. For what value of s is s equal to 0, well, it's 0. So we cover this up and we put s equal to 0 into everything that's left here, that goes here. So 9.81 divided by s plus 0, excuse me, so the s should be 0, because that's the value of s that makes s equal to 1, plus 0.025. So now I'm going to go and find my calculator, hopefully. Apologies. So we get 9.81 divided by 0.025, I get 392.4. Divided by s, and this is the same but divided by the negative. So you could write plus minus, and I'll do it here. Usually though, rather than writing plus minus, just write a minus here, same thing. Adding a negative is subtracting. And now we can send this back, because what we wrote up here was actually correct, it's just it couldn't be applied here. So we go from big V of s back to little v of t. The constant over s goes back to the constant. Now here I'm going to note that the plus minus, well, I'm going to fix the constant, the minus 392.4. Excuse me. And the 1 over s plus 0.025 goes back to e to the minus 0.025 times t. Done. Now there was a little supplementary question to this question, which was, what is the behavior of v of t? So what happens with the velocity for large values of t? What is the velocity when t gets big? So we'll write this as v goes to. So what happens to this little formula for the velocity when the time gets big? Well, nothing happens to this. It's just a constant. And now you need to understand this is a negative exponential. What happens with a negative exponential as t gets big? If you want to have a think, pause the video. A negative exponential goes to 0. So this term is 392.4 by something that goes to 0. So this goes to 0. So you're just left with the 392.4. I suppose if we're engineers, we want to look out for units. It actually doesn't say anything about units, so not a great question. So I won't include units here either. So 392.4 units. Okay. Now the next question we will probably look at in the next video.